Gravity is the silent sculptor of the cosmos. It is the force that gathers the dust of the early universe into stars, that binds stars into galaxies, and that weaves those galaxies into vast clusters stretching across the darkness. Without gravity, there would be no worlds to stand upon, no suns to light the sky, no moons to stir the oceans. Gravity is the architect of structure in a universe that might otherwise remain a drifting sea of particles, cold and without purpose. On Earth, we know gravity in its most familiar and gentle form. It is the reason a dropped stone falls to the ground. It is the reason our bodies have weight. At the surface of our planet, gravity pulls with a steady hand, just strong enough to hold oceans in their basins, to keep the atmosphere wrapped around the globe, and to let us walk without floating away. It is a force we take for granted, a background presence so constant that only when we leap, stumble, or fall do we remember its power. But the gravity that we feel here, measured as an acceleration of about 10 meters per second squared, is nothing compared to the monstrous extremes that lurk elsewhere in the universe. Our Earth is vast to us, yet its gravitational field is a whisper when set beside that of a collapsed star. Imagine a force not 10 times stronger, not 100, but billions and trillions of times greater. Imagine a place where the pull is so intense that not even light itself, traveling at nearly 300,000 kilometers per second, can escape once it strays too near. These are the realms of black holes, where gravity becomes not just a pull, but a devouring abyss. To understand the enormity of this difference, consider this. If you climb to the top of a mountain, your weight changes ever so slightly because you are farther from the center of Earth. The decrease is so small you could never notice it without instruments. Yet around a black hole, this simple truth of gravity, changing with distance, is magnified into something lethal. A difference of a few centimeters in your position can mean the difference between a survivable tug and an unstoppable rending. It is this differential pull that scientists call tidal gravity, and in the most extreme cases, it tears matter into threads. This fate has a name that sounds absurd at first, almost playful, but hides within it the most horrifying end imaginable: spaghettification. The word captures the image of a body stretched thin and long, like a strand of pasta. But what it describes is no joke. It is the death of matter itself under the grip of tides so violent that they rip atoms apart. Spaghettification is the final consequence of gravity pushed to its most extreme, a process where flesh, bone, molecule, and nucleus are pulled into a cosmic execution that leaves nothing of the original form intact. Here, at the edge of the greatest abysses in the universe, gravity ceases to be the gentle companion that lets us stand and becomes instead the predator of all structure. It is this duality that makes gravity both the most familiar and the most terrifying of forces. The same law that lets us build towers and launch rockets becomes the law that can dismantle stars and shred human bodies beyond recognition. And so, to glimpse why spaghettification happens, we must look closer at the true nature of gravity's reach. It is not enough to say that gravity pulls. We must understand that it pulls differently depending on where you stand. The head and the feet of a falling body are not pulled with equal force if the field is strong enough. This difference is the key to everything that follows. It is the reason why a journey toward a black hole is not a smooth descent, but a transformation, a distortion, and ultimately, a destruction. The gentle tide of Earth is our first clue. For even here we can feel the stretching power of gravity when we look to the oceans. The moon, small and distant though it is, raises bulges of water that sweep around the globe, creating tides that have shaped coastlines and guided human civilization for thousands of years. If such a small body can lift entire oceans, what might a collapsed star do to the very flesh and bones of a living traveler? That is the question that pulls us deeper into the abyss. What lies ahead is the journey from the ordinary pull of our Earth to the unimaginable pull of a black hole. Along the way, we will see how a familiar force becomes something alien, something that strips apart not only bodies but the very fabric of time and space. For once we enter the domain of extreme gravity, the rules we trust begin to break down. Light itself is bent, time itself is warped, and matter itself is stretched to its final thread. And at the heart of this, waiting for anything that dares to cross too close, is the shadow where no return is possible. Gravity is a sculptor that never sleeps. Across billions of years, it draws gas and dust into stars, fuses stars into galaxies, and binds those galaxies into sprawling webs. When you look up at the night sky, every point of light, every cluster, every sweeping arc of the Milky Way owes its existence to the ceaseless pull of gravity. And yet, the same force that paints the sky can also unmake its creations. Nowhere is this more evident than in the vicinity of a black hole. To appreciate how strange these regions are, it helps to step back and consider our own place. Here on Earth, we live under a constant pull, yet one that is forgiving. A child can jump and briefly resist it. Birds can spread wings and ride on air, defying gravity for minutes or hours. Even spacecraft, with enough speed and fire, can break free of Earth's pull and move into orbit. Gravity here is a companion, always tugging, but never inescapable. But imagine instead that you are falling toward a black hole. Unlike a fall on Earth, which lasts seconds before the ground interrupts you, this fall does not stop. There is no ground, no surface, only deeper layers of pull. The closer you draw, the faster you move, until speed itself becomes terrifying. If you were to fall feet first, your legs would feel a stronger tug than your chest, and your chest a stronger tug than your head. What starts as a gentle stretch quickly becomes an irresistible tearing. Within moments, your body would elongate, every part pulled with a different urgency. This is spaghettification in its earliest stage. It begins not with crushing, but with stretching. Unlike the idea of being pressed down by immense weight, the reality is more insidious. You are pulled apart, lengthwise, while being squeezed inward from the sides. Imagine a lump of clay pressed between invisible hands. It grows thinner and longer at the same time. This dual action is the essence of tidal gravity. It is not gravity itself that kills you, but the difference in gravity from one part of your body to another. On Earth, we barely notice this effect. The difference in gravity between your head and your feet is minuscule, so small that even the most sensitive instruments detect only the faintest variation. Our planet is too large, and we are too small for the effect to matter in daily life. But when you move closer to an object of immense density, that difference grows into a lethal force. Near a neutron star or black hole, a body can be stretched into strands before it even has time to register what is happening. The terrifying truth is that spaghettification can begin before you even cross the point of no return, the event horizon. To an outside observer watching you fall, your descent appears to slow, frozen in place as light struggles to escape the pull. To you, however, time continues as always, and with each passing second, the pull intensifies. The event horizon does not wait for you to cross before reminding you of the consequences. Long before that boundary is reached, your body can already be unraveling. This is the dual face of gravity. It shapes and it destroys. It makes planets and then swallows them. It forms stars and then feeds upon them. The same equations that let Newton predict the falling of an apple also describe the fall of a human body into a black hole, though the outcomes could not be more different. We live in a universe where the familiar becomes alien when pushed to its extremes. Consider the energy involved. To escape Earth's pull, a spacecraft must reach about 11 kilometers per second. That is already beyond anything a human body could endure unprotected. But to escape a black hole, no speed is enough. Even light itself, the fastest traveler known, cannot flee once caught. The pull is absolute. Once you pass the horizon, no path leads outward. All paths bend inward, leading inevitably to the core. What waits there is a mystery. Einstein's theory of general relativity predicts a singularity, a point of infinite density where space and time themselves collapse. But physics as we know it cannot fully describe this place. Our best equations falter, breaking into contradictions. And yet, whether or not the singularity exists as described, the fact remains that falling into a black hole is a one-way journey. For matter that crosses the boundary, the story ends not with compression into a point, but with disassembly long before that final step. It is this disassembly, this violent unraveling, that spaghettification describes. Bones stretch and break, flesh elongates, cells are torn from cells, molecules are split, atoms are drawn into streams of nuclei and electrons. What began as a person becomes a filament of matter, thinner and longer with every passing instant. Eventually, even that filament is consumed, drawn down into the unseen depths. And yet, there is a strange beauty in this. The universe does not waste. Matter devoured by black holes can be recycled, ejected in bursts of energy, or radiated away at the edges of the abyss. Stars have been torn apart this way, their remains cast outward as brilliant flares that astronomers can see across millions of light years. Even in destruction, gravity plays its role as a cosmic engine, redistributing matter and light into new forms. Still, for any living being caught in such a fate, the experience would be beyond imagination. To us, gravity is the steady pull that keeps our feet on the ground. To a traveler who strays too close to a collapsed star, gravity becomes the executioner that stretches them into nothingness. The lesson is clear. Gravity is not uniform. It is not a simple downward tug. It is a shape-shifting presence, growing stronger with proximity and capable of twisting the very geometry of space. When we speak of spaghettification, we speak of the most extreme revelation of this fact. And so we come to the threshold of understanding. We have glimpsed the difference between gentle earthly gravity and the abyssal pull of a black hole. We have seen how stretching, not crushing, is the true signature of this death. To go further, we must explore in detail how tidal forces work, why the difference in pull matters more than the pull itself, and how these forces can rise from imperceptible to overwhelming in the span of a few kilometers. This is where our journey now leads, deeper into the physics of tides, and closer to the edge where time, space, and matter are stripped bare. Falling toward a black hole is not like falling anywhere else. On Earth, gravity pulls us down at the same rate no matter our size or shape. A feather and a stone, if air is removed, drop side by side. The pull is uniform enough that everything nearby shares the same acceleration. But near a black hole, this sameness is shattered. The force is no longer gentle and even. It is a cliff face, a gradient so steep that the lower part of your body is pulled much harder than the upper part. The farther you fall, the more this difference grows, until it is unbearable. This is the essence of tidal gravity, and it is why spaghettification is not science fiction, but a real and unavoidable consequence of the laws of physics. The term may sound like a joke, but the reality is merciless. A human being falling feet first would feel their legs dragged away, their spine pulled taut, and their head trailing behind. The body becomes a thread, first elongated, then torn apart. To describe it clinically is simple. To imagine it happening to oneself is to stand on the edge of cosmic horror. Consider for a moment the ocean tides on Earth. Twice each day, waters rise and fall, drawn by the pull of the moon. These tides are mild compared to the ones created by a star's collapse. Yet even here, we see the truth that gravity acts differently at different distances. The side of Earth facing the moon is pulled more strongly than the far side, creating the bulge of high tide. The same principle, when magnified near a black hole, is what destroys a body completely. Now picture yourself in orbit around a black hole. At first, you circle safely, speed balancing pull, but with the smallest disturbance, you begin to spiral inward. You try to resist, but resistance is impossible. The closer you come, the faster you move, until resistance itself has no meaning. Soon, the difference in pull between your head and your feet is not just measurable, but catastrophic. In less than a heartbeat, you are stretched, your body becoming longer and thinner as invisible forces squeeze from the sides. From the perspective of someone watching from far away, your fall is eerily different. They would never see you cross the event horizon. Instead, they would see you approach it more and more slowly, fading into red as your light is stretched by the pull. To them, you seem frozen just above the boundary, never quite gone, a ghost locked in time. To you, however, there is no pause. Time feels normal, your descent relentless, and your body already unraveling long before you vanish from their sight. This duality is part of what makes black holes so unsettling. Reality itself divides into two perspectives, both valid, both inescapable. For the distant observer, you are trapped on the edge, stretched and fading. For you, the fall continues without interruption, your body yielding to the most extreme sculptor in the universe. Gravity is no longer a background force but an executioner, silent and absolute. And yet, even in this destruction, there is an echo of creation. Matter that falls into a black hole can heat the surrounding space, forming an accretion disk that glows brighter than entire galaxies. Particles torn from infalling matter can be hurled outward in jets that span light years. The same process that ends the story for a traveler can light up the cosmos for others to see. This is the paradox of gravity's darkest grip. What it consumes in silence, it announces in brilliance. The phrase point of no return is often used to describe the event horizon, but in truth, the unraveling begins earlier. The limits of the human body, of bones, cells, and molecules, give way before the horizon is reached around small black holes. Spaghettification does not wait politely at the boundary. It begins when the difference in pull between head and foot grows too strong, and that can happen well outside the horizon for stellar mass black holes. Only the largest supermassive black holes offer a different fate, where you may cross the horizon intact, only to meet destruction deeper within. It is here that we encounter the most haunting lesson of all. Gravity is not only the builder of worlds, but their destroyer. It is not content merely to hold you down. It pulls at every part of you, differently, relentlessly, until structure itself is gone. The end is not a crushing weight, but an elongation beyond recognition, a transformation of matter into a thread. Spaghettification is the ultimate revelation of what gravity can do when it is pushed to its furthest extreme. This chapter has traced the journey from the familiar to the unimaginable, from the gentle tug that lets us walk to the abyssal pull that unravels us thread by thread. We have seen gravity's dual nature, creator and destroyer, sculptor and executioner, and we have glimpsed the fate that awaits anything that dares approach too closely to a collapsed star. But to truly understand why this happens, to move beyond imagery and into the mechanics, we must look closer at the mathematics of tides. The same principle that explains the swelling of Earth's oceans also explains the tearing of matter near a black hole. The next step in our journey is to explore how tidal forces grow, how they act upon bodies, and why they shift from gentle to lethal. And so we end here, on the threshold of understanding. We have introduced the idea of spaghettification and felt its dread. Ahead lies the science that explains it, the laws of gravity stretched to their breaking point. In the next chapter, we will see how the tides of Earth scale upward to the tides of collapsed stars, and how a familiar rhythm of the seas becomes, at the edge of a black hole, the rhythm of destruction. Gravity is often spoken of as if it were a single and uniform tug, but this is a simplification born of daily experience. The truth is subtler and far stranger. Gravity is not only about how strong the pull is, but how that pull changes with distance. It is this change, this difference, that shapes the rise and fall of oceans, the stretching of bodies, and ultimately the unmaking of matter itself in the depths of black holes. This difference is what physicists call tidal forces. And to understand spaghettification, we must first understand them. Imagine Earth and its oceans. The moon hovers in space at a distance of nearly 400,000 kilometers, far smaller than Earth but close enough to matter. The moon's pull on Earth is not uniform. The side of Earth facing the moon feels a slightly stronger tug than the far side. Oceans flow in response, drawn into bulges that rotate around the globe. Twice each day, the water rises and falls, and civilizations throughout history have lived by this rhythm, timing voyages, harvests, and rituals to the pulse of the tides. This familiar phenomenon is the most accessible demonstration of tidal gravity, but tides are not limited to oceans. The very rock of Earth shifts slightly under the moon's pull. The crust flexes, the atmosphere responds, and even the core is stirred. Our planet is resilient enough that these changes are small, but the principle is the same. When gravity varies across space, it stretches one side and relaxes the other. The result is motion, bulging, straining. The ocean tide is only the most visible example. Now take this principle and carry it outward into the wider universe. Picture a moon orbiting a giant planet like Jupiter. The immense pull of that planet exerts such strong tides on its moons that ice is cracked, volcanoes erupt, and entire surfaces shift over geological time. Io, one of Jupiter's largest moons, is a tortured world of constant volcanic activity, its interior kneaded and heated by relentless tides. Europa's icy crust flexes and fractures, hiding beneath it an ocean that may be kept liquid by tidal heating. What we see there is the quiet but immense power of gravity differences. Scaling upward again, think of stars near dense companions. When two stars orbit closely, one may pull material from the other, drawing its surface into a teardrop shape. Matter streams from one star to the other, feeding it, reshaping it, altering its evolution. Tidal forces are not passive curiosities. They are engines of change, sculptors of orbits, destroyers of stability. The physics behind this is simple in its essence, but profound in its consequences. Gravity weakens with distance, but it does not do so in a straight line. The strength of the pull is proportional to the inverse square of distance. This means that if you double the distance from a body, the pull becomes not half as strong, but 1/4. If you triple the distance, the pull becomes 1/9. This sharp decline is what makes differences noticeable. When your feet are closer to a black hole than your head, the change in distance is enough that the pull is measurably stronger at one end than the other. That difference is the tide. On Earth, the difference is minuscule. Between head and foot, it is so tiny that we never feel it. But the closer you are to a massive body, the more extreme it becomes. Near a neutron star, only about 20 kilometers across, yet heavier than our sun, tidal forces rise to brutal levels. A human approaching such a star would be stretched beyond recognition long before touching its surface. Near a black hole, the effect grows still more unforgiving. The beauty of tidal forces is that they reveal gravity's true nature as a geometric influence. It is not simply a downward tug, but a bending of paths, a reshaping of trajectories. When space itself is curved by mass, the lines along which bodies fall diverge or converge depending on their separation. A cluster of points that begin together can be pulled apart into threads. This is why astronauts in orbit feel weightless, even though they are still under Earth's pull. Everything around them falls together, sharing the same acceleration, so there is no relative force between them. But if they were falling toward a black hole, that sameness would vanish. The small difference in position would grow into a destructive difference in pull. Tidal forces are therefore the hinge upon which spaghettification turns. They are the quiet beginning of a violent end. We see their gentlest forms in the ebb and flow of seas, their moderate forms in the fractures of icy moons, their stronger forms in the distortion of stars, and their ultimate forms in the unraveling of bodies near collapsed remnants of stellar death. And so, when we ask why spaghettification happens, the answer is found here, in the physics of tides. Gravity is not just about strength, but about change. It is not how hard the universe pulls on you, but how differently it pulls on your parts. That difference, magnified by density and proximity, is the root of cosmic stretching. This is the lesson that leads us deeper still. For if tides can shape oceans, knead moons, and strip stars, what do they become when unleashed in the presence of something so dense and merciless that even light cannot flee? The answer is that tides cease to be a force we can survive and become instead the most efficient destroyer in nature. To stand on the shore and watch the ocean rise and fall is to witness the quiet breath of tidal gravity. It is gentle enough to guide sailors, to wash shells onto beaches, to mark the rhythm of life along coastlines. Yet within that steady rhythm is hidden the seed of one of the most terrifying forces in the cosmos. The principle is simple. One side of a body is pulled differently than the other. This difference, though mild on Earth, can scale into violence when the masses involved are immense and the distance is small. Consider again the moon pulling at Earth. The gravitational attraction is slightly stronger on the side facing the moon and slightly weaker on the far side. Oceans respond, stretching outward into two bulges, one toward the moon and one away from it. As Earth rotates beneath these bulges, we experience two high tides and two low tides every day. The mathematics that describe this cycle are the same mathematics that describe the stretching of a human body falling toward a black hole. The difference is only in scale. If the moon were closer to Earth, the tides would be catastrophic. Imagine the moon hovering at half its current distance. The pull would be not twice but many times stronger, because gravity decreases with the square of distance. Continents would flood, oceans would surge over land, and coastlines would be erased. Tidal forces would remake the planet. This hypothetical disaster is but a hint of what actually happens near collapsed stars. In the outer regions of the universe, we find neutron stars, the remnants of massive stars that exploded in supernovae. A neutron star packs more mass than our Sun into a sphere only about 20 kilometers wide. At such density, a teaspoon of neutron star matter would weigh billions of tons. The tidal forces near one of these objects are unimaginable. If you were to fall toward its surface, the difference in gravity across your body would become lethal long before you touched down. You would be torn apart in midair, elongated and shredded by forces no bone or tissue could resist. And yet, even neutron stars pale beside black holes. A black hole compresses matter into an even denser state. When you approach a black hole, there is no surface to strike, no ground to break your fall. There is only the gradient of gravity, growing sharper and sharper as you descend. It is here that tidal forces reach their true crescendo. The same principle that pulls oceans into bulges pulls human bodies into filaments. The mathematics remains simple. Gravity grows stronger as you approach, and the difference between head and foot grows faster still. This difference is not just a matter of perception. It is measurable, calculable, a direct consequence of Newton's law of universal gravitation and Einstein's refinement in general relativity. If your feet are closer to the black hole than your head, the pull on your feet is stronger. The greater the difference, the greater the stretch. At first, your spine resists, your muscles strain. But gravity does not tire. With every fraction of a second, the difference grows until resistance breaks. Imagine the sensation. At first, a faint elongation, perhaps a pressure in the legs. Then a tearing as tissues separate, joints wrench apart, and bones snap. But the process does not stop at the body. Molecules themselves are pulled, bonds strained, until they break. Atoms are stripped, nuclei separated from electrons. What began as a person ends as a ribbon of subatomic debris drawn into the depths. This is not speculation. It is the unavoidable result of physics as we know it. Some may wonder why astronauts in orbit around Earth do not feel this stretching. The reason is that orbital motion shares the same acceleration as the spacecraft itself. Everything inside falls together, equally, and so no relative force is felt. This is what we call free fall. But near a black hole, the difference in pull between nearby points grows so steep that free fall no longer protects you. The parts of your body fall differently, and free fall itself becomes fragmented. It is not a fall in unison, but a fall in pieces. Astronomers see the consequences of tidal forces on scales far beyond the human body. Stars themselves are sometimes unlucky enough to wander too close to black holes. When this happens, the star is pulled into a teardrop shape, elongated until it is torn apart. The debris forms a swirling disk, heated to incandescence, shining across millions of light years. We call these cataclysms tidal disruption events. They are spaghettification writ large, the same principle that tears apart a human body, acting instead upon entire suns. In every case, from ocean tides to shattered stars, the rule is the same. The pull of gravity changes with distance. Where that change is gentle, we get tides that guide the cycles of Earth. Where it is extreme, we get destruction, so violent that structure itself cannot endure. Spaghettification is therefore not a mystery, but an inevitability. It is not something separate from tides, but tides in their most absolute form. As we deepen our journey into this subject, the lesson becomes clearer. The same gentle force that lifts waves on beaches can, under the right conditions, destroy matter at every scale. The laws of physics are consistent. What differs is only the stage upon which they act. On Earth, that stage is calm. Near a black hole, it is fatal. And so, to see why black holes have the power to unmake matter so completely, we must continue to follow the logic of tides. We must look at how they intensify with shrinking distance, how they warp bodies in motion, and how, at the boundary known as the event horizon, they decide the difference between survival and annihilation. Tidal forces are the hidden sculptors of fate near black holes. To grasp their inevitability, imagine walking along a line of steepening cliffs. At first, the slope is gentle. You can stroll with ease, feeling only a mild incline. But with every step forward, the slope grows sharper until it is no longer a slope but a wall, and then beyond that, a sheer drop into darkness. Gravity behaves in much the same way. At a distance from a black hole, the gradient is mild, almost invisible, but as you draw closer, it rises with terrifying speed, until a difference of only a few centimeters can mean the difference between life and dissolution. The mathematics of this steepening is rooted in the geometry of space. Gravity is not just a force, but the bending of space-time itself. Objects follow curves written into the fabric of the universe. When mass bends space, the paths of nearby objects converge or diverge. If you and another traveler fall side by side toward a black hole, the lines of your descent do not remain parallel. They draw together, crossing, twisting, stretching. You would feel as if invisible strings were tugging you apart, though in truth, it is the very geometry of space that is unweaving your form. This is why tidal forces cannot be resisted indefinitely. Muscles may strain, bones may resist, but geometry itself is stronger. It is the shape of space-time that dictates how you fall. Resistance is like trying to stop the tilt of the Earth or the spin of the galaxy. No matter your strength, the outcome is written in the structure of reality. The difference between tidal forces on Earth and those near a black hole is not a difference in kind, but in degree. On Earth, the variation is so slight that we barely notice it. The oceans rise and fall, rocks flex by a fraction of a millimeter, and our bodies feel nothing at all. But shift the context, reduce the scale of distance, and suddenly the same principle becomes the destroyer of worlds. This continuity is both elegant and chilling. The same laws that guide the tides also dictate the shredding of matter. Imagine a spacecraft daring to approach the edge of a black hole. Its crew watches instruments shift as gravitational differences grow sharper. At first, the stretching is gentle, an elongation of orbit, a strain on structure. But as the craft dips lower, the variation across its length becomes immense. The hull groans, rivets pop, panels buckle. Even steel and titanium, forged to withstand unimaginable pressures, cannot endure the gradient. The ship unravels before it reaches the horizon. The crew, caught inside, meet the same fate. The vessel becomes a filament of matter, each fragment falling on its own path, no longer a whole, but a stream of debris. This vision is not fantasy. Astronomers have watched stars experience this fate. Entire suns pulled apart into rivers of gas, stretched and funneled into accretion disks that blaze like cosmic bonfires. These events are among the brightest beacons in the universe, outshining galaxies for brief moments. In their light, we read the truth of tidal destruction. What happens to stars on a vast scale happens to smaller bodies as well. A person, a spacecraft, even a planet, all would meet the same unraveling if they ventured too near. The beauty of this realization lies in its symmetry. Gravity is universal. It does not distinguish between the smallest grain of dust and the mightiest star. Both obey the same law. Both are subject to the same tidal differences. The universe is impartial, its rules indifferent to scale. It is we who interpret the consequences as gentle or terrible, depending on our place within the gradient. And yet, even within this impartiality, there is variety. Not all black holes tear you apart in the same way. A stellar mass black hole with only a few times the mass of our sun creates lethal tides outside its horizon. A human traveler would be unraveled before crossing the boundary, shredded in open space. But a supermassive black hole, millions or billions of times the mass of the sun, behaves differently. Its horizon lies so far from its center that the gradient there is mild. A traveler might cross the horizon intact, only to be destroyed deeper within. The difference lies not in the rule, but in the scale. The same mathematics produce different fates depending on size. This distinction is what makes tidal forces both fascinating and terrifying. They are not merely destructive. They are precise, governed by the mass and radius of the body involved. For some black holes, the fatal stretching begins outside the horizon. For others, the horizon swallows you whole before the process starts. In either case, the outcome is final, but the timing, the location, the details of the unraveling all depend on the dance between mass and distance. To think of this is to realize that spaghettification is not a random horror, but an orderly consequence of the universe's laws. It is the most extreme expression of tides, the same process that guides Earth's oceans written on a cosmic stage. The transition from harmless to lethal is seamless. There is no break in logic, no contradiction, only a continuous amplification of the same principle until it becomes irresistible. And so, at the end of this chapter, we stand at the edge of the event horizon, the place where tides are poised to decide our fate. We have traced the journey from gentle ocean swells to the catastrophic elongation of stars. We have seen how a familiar rhythm becomes an instrument of destruction. What remains is to step closer, to cross into the domain where even light cannot escape, and to witness how spaghettification begins its work before and after the horizon is passed. Ahead lies the point of no return, where tides rule absolutely, where descent becomes destiny. In the next chapter, we will cross that boundary, guided by the same laws we have now uncovered, and confront what it truly means to fall into the heart of a black hole. There is a boundary in the universe, unlike any other, a frontier where the familiar laws of space and time bend into strange new forms. This boundary is called the event horizon. It is not a physical surface, no wall of stone or fire, no glowing ring or burning edge. It is an invisible frontier in space-time itself. To cross it is to surrender forever, for beyond it no signal, no light, no cry for help can ever escape. The event horizon is the ultimate one-way door. To understand why, imagine falling. On Earth, if you leap from a height, gravity accelerates you until the ground stops your descent. If there were no ground, you would simply continue, faster and faster, though in reality, air resistance would resist you. Now imagine falling where there is no air and no ground, only a pull that grows stronger as you descend. This is what happens near a black hole. You accelerate endlessly, drawn deeper into the pit, until the speed needed to escape becomes greater than the speed of light. And because nothing can outrun light, escape becomes impossible. The event horizon is therefore not just a distance, but a limit written into space-time. It is the place where every path forward bends inward. Every possible future leads closer to the center. Outside the horizon, you can still turn away, fire engines, aim outward, and escape if you have enough speed. Inside, no effort matters. Even light itself is trapped. To fall past the horizon is to commit to a journey with only one ending. But here lies a subtlety. The act of being torn apart by tidal forces does not wait politely until you cross this threshold. In the case of stellar mass black holes, the stretching begins well outside the horizon. If you fall feet first, your legs feel the pull more strongly than your chest, and your chest more strongly than your head. The difference grows with every moment, and soon the body cannot endure. Bones snap, tissues tear, organs elongate. You are destroyed before you even reach the boundary. The horizon swallows what is left. Not a person, but a ribbon of debris. To an outside observer, however, the story looks utterly different. Imagine your companion watching you fall from a safe orbit. From their perspective, your descent slows as you approach the horizon. Time itself seems to falter. The signals from your body, the light reflecting from your skin, all stretch into longer wavelengths, fading into red. You do not appear to cross. You freeze just above the invisible line, dimming, elongating, becoming a ghost of yourself. To them, you never vanish. To you, the plunge continues uninterrupted. Both perspectives are real. Both are true. And together, they paint one of the strangest pictures in physics. This duality is what makes the event horizon not just a physical frontier, but a conceptual one. It challenges the very idea of a single reality. Are you frozen at the edge, dimming into eternity? Or are you falling inward, unraveling, racing toward destruction? The answer depends on where you stand, outside or within. The universe allows both to be true, even though they seem contradictory. For you, the traveler, there is no pause, no freeze. The fall continues. The stretching grows worse. Every second, the difference in pull between your head and your feet increases, and your body becomes longer and thinner. Time, as you feel it, ticks forward as usual, your heartbeat racing, your thoughts struggling to keep pace. Yet to those outside, your heartbeat slows, your signals stretch, your very image fades. The black hole is a stage upon which two versions of the same event are played at once. This is the strange beauty of relativity. It does not deny either experience. Both are valid. Both arise from the same laws. Reality is not singular but layered, perspective woven into the fabric of existence. The event horizon is therefore not only the point of no return, but also the point where reality itself divides, where what is true for you diverges from what is true for others. And still, beneath this strange dance of time and perspective, the physical truth remains. Whether outside or within, spaghettification is underway. The very geometry of space ensures it. The closer you fall, the sharper the gradient. The sharper the gradient, the greater the stretch. For stellar black holes, that stretch becomes fatal before the horizon is crossed. For supermassive black holes, the crossing comes first, the destruction later. But in every case, the end is written. Once begun, the process cannot be stopped. This is what it means to approach the point of no return. It is not only a boundary in space, but a boundary in fate. To cross it is to accept the final unraveling. To hover near it is to be seen differently by every observer. The horizon is not merely the edge of a black hole. It is the edge of meaning, the place where physics and perception combine to reveal the limits of what we can know, and so we step closer, drawn by curiosity and dread alike. The next stage of our journey is to see how this process unfolds in detail, how a fall becomes an elongation, how perspective splits into two truths, and how the nature of the black hole itself decides whether you are torn apart before the crossing or devoured whole beyond it. To imagine the fall more clearly, place yourself in the position of a traveler daring to approach the abyss. You drift closer, drawn inward by a pull that grows stronger with every passing moment. At first, it feels like any other descent, the kind an astronaut might feel when orbiting a planet. The stars above you remain still, the black hole ahead, a dark void blotting out the heavens. But soon, subtle changes begin to stir. You are falling feet first, and your legs feel the tug before your chest does. The pull at your feet is slightly greater, and with every kilometer it grows more pronounced. Muscles strain as if against invisible weights, your spine tightening, your head pulled backward in resistance. What begins as discomfort becomes pain, and pain becomes tearing. The body that once moved as a whole is no longer treated as one by the universe. Each part is pulled according to its place in the gradient. This is the beginning of spaghettification. It is not a crushing downward blow, as in popular imagination, not the weight of 1,000 Earths pressing down, but something stranger. You are stretched like taffy, elongated into a shape you no longer recognize. At the same time, you are squeezed inward from the sides. Your chest narrows, your shoulders press inward, your organs are compressed. Gravity does not simply pull, it stretches in one direction and squeezes in the other. You are not merely falling, you are being reshaped by the geometry of space-time itself. Outside observers, if any are watching, see a very different picture. To them, you slow as you approach the horizon. The signals from your body weaken, the light from your skin and clothing shifts to red, dimming into darkness. Your final moments, as they see them, stretch into eternity. They do not see the tearing. They do not see your descent inside. For them, you are caught on the edge, fading into a ghostly afterimage that never quite disappears. But your experience is unrelenting. Time flows normally for you. Seconds pass. Your heart races. Your mind struggles to comprehend what is happening. The stretching intensifies with every instant. If you had instruments, you could measure the difference in pull between your head and your feet. That difference is the tidal force, the precise number that tells you how quickly your body is being pulled apart. For small black holes, this number grows so large so quickly that your body is destroyed long before you even cross the horizon. For larger black holes, the gradient is more gentle at the horizon, and you may pass through still intact, though the destruction will follow inside. Here lies the subtle but crucial truth. The event horizon is not the moment of death, it is the moment of inevitability. Death by spaghettification can come earlier or later, depending on the mass of the black hole, but once you pass the horizon, no force in the universe can prevent it. You may survive the crossing in one piece, but your fate is already sealed. The laws of geometry and gravity are not negotiable. Consider a stellar mass black hole, the kind formed when a massive star collapses. Its horizon may be only a few kilometers across. The gradient outside is immense. For such a black hole, the difference in pull across a human body becomes fatal long before the horizon is reached. You would never live to see the crossing. You would be stretched into ribbons of matter in the space outside, your remains swept across the horizon as debris. Now consider a supermassive black hole, the giants found in the hearts of galaxies. These are millions or billions of times more massive than our Sunday. Their horizons stretch across millions of kilometers. For such a colossus, the gradient at the edge is relatively mild. You could cross the horizon without noticing anything dramatic at first. Only once you fall deeper toward the center do the tides intensify enough to destroy you. In this case, the horizon is crossed while you are still whole. But that wholeness is temporary. Both fates are real. Both arise from the same laws. The difference is only in scale. Stellar black holes kill before the horizon. Supermassive black holes kill after. In every case, the end is the same: spaghettification and dissolution. The inevitability of this process is what gives the event horizon its fearful name. It is not merely a boundary of visibility, but a boundary of destiny. Once crossed, every path leads inward. You may still be alive, you may still feel, think, and see, but you cannot turn back. Your entire future has narrowed to a single end. The horizon is not a wall of fire or a sudden blast of energy. It is a silent decree written into the structure of space-time. And yet, for all its horror, the process is strangely serene in appearance. From the outside, nothing violent is seen. No explosion, no sudden break, only a fading into red and then into black. The violence is hidden, reserved for the traveler inside. This contrast makes the event horizon one of the most haunting features of the cosmos. To observers, it is calm. To participants, it is the end of all structure. The lesson of the point of no return is that physics does not bend for us. The laws that govern oceans and planets also govern black holes. They are impartial, indifferent, exact. The same tides that move water across beaches also move bones, molecules, and stars. At the event horizon, this continuity reaches its most extreme form. We are left, then, with a profound paradox. To watch someone fall is to see them never quite arrive. To fall oneself is to experience the journey to its final conclusion. The horizon divides not only space, but reality itself. Two truths coexist, never reconciled. This duality is not an illusion, but the nature of relativity. The universe does not promise us a single narrative. It gives us many, depending on where we stand. And as the traveler continues to fall, as the differences in pull grow sharper, the process accelerates. Soon the distinction between outside and inside, between horizon and beyond, becomes irrelevant. The stretching has begun, and once begun, it cannot be stopped. The moment of crossing is unlike anything else in nature. There is no visible line, no barrier you can see or touch, no sound to mark the instant. Yet in that silent passage you have left one universe behind and entered another. Outside the horizon, escape was still possible. Inside, every path, every future, every heartbeat leads inward. The event horizon is less a place than a fate. To the distant observer, you never cross it. They watch you fade, your light stretched thinner and redder, until it slips beyond their reach. Your image lingers on the edge, ghost-like, frozen. To them, your last breath never ends. Your fall never completes. To you, however, the experience is seamless. There is no pause, no halt, only descent. You pass the horizon without resistance, without fanfare. In that instant, your story becomes two stories, one written on the outside, one carried with you into the dark. Inside, the pull does not slacken. It grows, sharpening with every fraction of distance. The stretching intensifies. The squeezing from the sides presses harder. Your body becomes less a body and more a thread, elongated, drawn into a filament finer than any material known. This is not a violent explosion, not a tearing apart with sound and shock, but a relentless transformation. It is slow in appearance, yet fast beyond comprehension. Atoms themselves do not hold. Their bonds break, their nuclei scatter, their essence reduced to streams of matter, guided by the geometry of space-time. This is the core truth of spaghettification. It is not an impact or a strike, but a process of differences. Your feet fall faster than your head. Your sides collapse inward, while your length stretches outward. Geometry dictates every step, and there is no force, no technology, no effort that can counter it. Against a planet, you may resist with rockets. Against a star, you may resist with distance. Against a black hole, there is no defense. Once the threshold is crossed, every outcome is set. The paradox deepens when you realize that for large black holes, the crossing itself may not destroy you. A supermassive black hole with millions or billions of solar masses stretches its horizon across millions of kilometers. At that immense scale, the gradient at the horizon is gentle enough that your body feels little difference between head and feet. You may cross the event horizon intact, not knowing the line has been passed. Only deeper inside, as you approach the center, do the tides rise to fatal levels. Yet for stellar mass black holes, the opposite is true. Their horizons are tiny, measured in kilometers, their gradients fierce. Here, you would be stretched and destroyed before the horizon itself, never living to cross it whole. The distinction is haunting. The same laws of physics dictate two fates, separated only by scale. The same doorway can either consume you whole or tear you apart before you enter. This is what makes the point of no return so strange. It is not a single experience, but many, depending on the size of the black hole, the path of your fall, and the perspective of those who watch. In every case, though, the end is the same. Beyond the horizon lies dissolution. Beyond the horizon lies the breaking of structure, the unwinding of matter, the spaghettification of everything that falls. It is here that gravity reveals its dual role most starkly. On Earth, it binds oceans, holds air, anchors our lives. Near black holes, it dismantles, strips, and consumes. The same law, expressed differently, builds worlds and destroys them. This continuity is as awe-inspiring as it is terrifying. To contemplate the event horizon is to contemplate the limits of knowledge. Once matter passes it, no information returns. To outsiders, the horizon hides all. To the traveler, it hides nothing, not yet. But both agree on the outcome. Inside, there is no path back. Outside, there is no way to see within. The boundary is absolute. And so Chapter 3 closes with a vision of that frontier. A place where time splits into two truths, where perspective diverges, where fate is sealed. Ahead lies a deeper exploration of how the kind of black hole you fall into decides the details of your destruction. Stellar mass black holes kill before the horizon. Supermassive black holes swallow you whole and destroy you later. Both lead to the same unraveling, but their paths are different. In the next chapter, we will see how size reshapes destiny, how the very scale of collapse determines whether spaghettification strikes outside or inside, and how Einstein's relativity makes this difference stranger still. We move from the point of no return to the question of what kind of black hole awaits, and how it will choose the manner of your end. Not all black holes are equal. Some are born from the collapse of massive stars, leaving behind horizons no larger than a few kilometers. Others sit in the hearts of galaxies, millions or billions of times more massive than the Sun, horizons vast enough to engulf planetary systems. Both are black holes. Both bend space-time so severely that not even light can escape. Yet the experience of falling into them could not be more different. The scale of their gravity decides how and when spaghettification claims you. Let us begin with the smaller kind. A stellar mass black hole forms when a star many times heavier than our Sun exhausts its nuclear fuel and collapses under its own weight. The core implodes, the outer layers explode in a supernova, and what remains is a compact object so dense that its gravity becomes absolute. Its event horizon may span only a handful of kilometers, but within that narrow distance, the gradient of gravity is brutal. If you were to approach such an object, spaghettification would strike before you ever crossed the horizon. The difference in pull between your head and your feet would grow unbearable, and your body would elongate and break apart outside the boundary itself. In this case, the event horizon is not the moment of destruction, but the moment that consumes what is left. For stellar black holes, the violence begins earlier. The gradient is simply too steep, the distance too small for anybody to endure. Now shift the scale to supermassive black holes, the titans of galactic centers. Their masses are millions to billions of times greater than the sun. Their horizons stretch across millions of kilometers. To fall into one of these giants is a different story. At such enormous scales, the pull at the horizon is not sharp, but gradual. The difference in gravity across the length of a human body is small. You could drift across the boundary without noticing anything unusual. There would be no tearing yet, no agony, no sudden awareness of having passed the ultimate frontier. You would fall in silence, intact, unaware that you had already crossed the line from which no return is possible. But make no mistake, the destruction would still come. The difference is only one of timing. Deeper inside, as you move closer to the center, the gradient sharpens. The same forces that rip bodies apart outside the horizon of stellar black holes will rip you apart inside a supermassive black hole. The outcome is the same. The path to that outcome is what changes. This distinction between small and large black holes illustrates a deeper truth about gravity. The same law applies in every case, but scale alters the experience. A gradient that is lethal at one distance may be survivable at another. The size of the black hole stretches the stage upon which the play unfolds. In one case, the act of spaghettification begins in open space. In the other, it begins after you have already passed the horizon, hidden from the universe outside. The difference also affects how we imagine these encounters. A stellar black hole is like a predator that tears its prey before swallowing. A supermassive black hole is more like a leviathan that engulfs its victim whole, letting the destruction happen unseen in its depths. Both consume utterly, but one shows its violence outside, while the other hides it within. For astronomers, this distinction matters in what we can observe. When a star wanders too close to a stellar black hole, its tearing happens in the space outside, producing flares and debris we can detect. With supermassive black holes, the initial swallowing may appear calm, the star slipping beneath the horizon before the real violence begins. Only when the debris emerges, heated and ejected, do we see the evidence of destruction. Even in observation, the scale of the black hole determines the face it shows to the universe. And for a human traveler, the difference is the difference between agony before the horizon and illusion of safety beyond it. Both paths lead to the same end, but the journey feels different. The stellar black hole ends you before you ever touch its frontier. The supermassive black hole lets you cross it whole, only to end you later when escape is already impossible. This is the haunting lesson of scale in the cosmos. The same laws govern all black holes. The same equations dictate their pull. Yet their size reshapes how those laws play out, deciding the place and timing of destruction. The traveler cannot alter the ending. Only the stage upon which it occurs is different. And in that difference lies the next layer of strangeness. For Einstein's theory of relativity deepens the paradox. To fall into either type of black hole is not only to be stretched or destroyed, but also to experience time and space in ways that defy common sense. The way we see spaghettification depends not just on size, but on the very structure of space-time, as relativity describes it. Imagine hovering at a safe distance from a stellar mass black hole. It is invisible, a darkness against the stars, yet its presence is betrayed by the violence around it. Gas from a nearby star spirals inward, heated to millions of degrees, glowing in X-rays, before vanishing into the abyss. The black hole itself remains unseen, but its appetite cannot be hidden. Now imagine daring to approach. The horizon lies only a few kilometers across, but the gradient of gravity is so steep that long before you reach it, your body begins to feel the strain. Your legs, slightly closer to the black hole, accelerate faster than your chest. Your chest, in turn, accelerates faster than your head. The difference is not gentle. It is exponential, growing sharper with every instant. At first, your body resists, muscles tightening, spine straining. But the forces grow beyond biology, beyond chemistry, beyond the very bonds of atoms. Before you have crossed the horizon, you have already been transformed into a stream of matter. For stellar black holes, the event horizon is not the place of destruction, but the place that swallows what remains of destruction's work. Now shift your imagination to a supermassive black hole at the center of a galaxy. Here the story begins differently. Its horizon may stretch millions of kilometers, larger than the orbit of planets. The gradient at its edge is surprisingly mild. You could cross the horizon without noticing. Still whole, still alive, still thinking you have time. You have, in fact, already passed the point of no return, but the tidal differences at the boundary are too small for your body to detect. To you, the fall feels eerily calm. This illusion of safety is what makes supermassive black holes deceptive. Crossing the horizon of a stellar black hole is fatal before it happens. Crossing the horizon of a supermassive black hole may feel uneventful, yet the end is no less certain. As you sink deeper, closer to the singularity hidden inside, the gradient grows sharper. What began as calm becomes unbearable. The same stretching that tore you apart outside a stellar black hole now strikes inside a supermassive one. The difference is only in when, not if, the destruction comes. This difference in timing arises directly from scale. A stellar black hole packs the mass of a sun into a sphere only a few kilometers wide. The pull changes so drastically over such a short distance that the difference across a human body is immediately lethal. A supermassive black hole spreads its mass across a horizon millions of kilometers wide. The pull there is enormous, but it changes more gently over the space of a body. Only deeper within does the difference rise to lethal levels. Both objects obey the same laws. The outcomes are the same. The stage upon which they play out is what changes. For astronomers, this distinction reveals itself in observation. When a star is devoured by a stellar black hole, its dismemberment occurs outside the horizon. Gas is stretched and heated, flaring brightly, visible to telescopes across the universe. When a star falls into a supermassive black hole, much of the violence happens inside the horizon, unseen. Only later do the echoes emerge, in the form of jets of energy or flares from heated debris, escaping the surrounding disk. Even nature herself observes the difference. One shows its destruction openly, the other hides it within. For the traveler, the emotional impact of this distinction cannot be overstated. To fall toward a stellar black hole is to meet death before even reaching the ultimate boundary. To fall toward a supermassive black hole is to cross that boundary intact, perhaps without even realizing it, only to discover too late that survival was an illusion. In one case, you are destroyed at the edge. In the other, you are swallowed whole and undone in silence inside. The paradox deepens further when relativity enters the picture. For the observer watching from afar, both journeys look eerily similar. In either case, you appear to slow as you approach the horizon, your signals stretching into red, your image fading. To them, you never cross, whether the black hole is small or vast. To you, the experience diverges sharply. In one scenario, you are torn apart outside. In the other, you pass through whole, carrying with you the secret that you have already fallen past the point of no return. This contrast between perception and reality, between scale and fate, is part of what makes black holes among the strangest objects in the universe. They are governed by the same mathematics, yet the experience they provide depends entirely on size. Scale decides whether you are destroyed in open space or inside the horizon. Relativity decides whether others see you cross at all. In every sense, black holes are reminders that the universe does not conform to human expectation. And yet, in both cases, spaghettification rules in the end. There is no path where you remain whole forever. The laws of physics are impartial. Whether you are torn before the horizon or after it, whether your destruction is seen or hidden, the outcome is dissolution. Matter cannot survive infinite gradients. Structure cannot endure infinite stretch. Black holes, large or small, enforce the same truth in their different ways. To weigh the fate of stellar and supermassive black holes side by side is to see two versions of inevitability. The laws of physics are the same, yet the stage they play upon is different, and the manner of destruction shifts with it. One rips you apart before you can reach its frontier, the other allows you to pass through whole, only to unravel you later in silence. Both lead to the same end, yet the journey feels profoundly different. A stellar black hole is an intimate predator. Its event horizon may be only a few kilometers across, yet its power is absolute. If you fell toward it, you would not live to reach the horizon. The gradient across your body becomes lethal in open space. It does not wait for you to cross the one-way door. It acts early, pulling you apart atom by atom, until what enters the horizon is no longer a human traveler, but a thin stream of matter. To die in this way is to be unmade in public view, torn outside, your final fate, visible to the universe. A supermassive black hole, in contrast, is a silent giant. Its horizon can stretch across millions of kilometers. Its gradient at that scale is deceptively gentle. You could cross the horizon unaware, your body intact, your mind still thinking of possibilities. And yet, once inside, the future is no longer yours. The descent continues, deeper and deeper, the differences in pull growing sharper until they become unbearable. In the belly of this giant, spaghettification waits patiently. To die in this way is to be unmade in private, your final fate hidden from all outside eyes. The paradox is striking. Two objects governed by the same equations produce such different experiences. The distinction lies in size, in scale, in how density spreads across distance. It is a reminder that physics is both universal and subtle. The same principles can paint radically different pictures, depending on context. For black holes, context is everything. For astronomers, these differences shape the stories they can tell. A star devoured by a stellar black hole is shredded outside the horizon, producing luminous flares that blaze across space. A star devoured by a supermassive black hole vanishes more quietly, its dismemberment occurring mostly inside the horizon. We see only echoes, jets, flares, debris streaming from the surrounding disk. The universe reveals one kind of destruction openly and hides the other behind the curtain of space-time. For a human traveler, the distinction is more visceral. A fall into a stellar black hole is a death of violence at the edge. A fall into a supermassive black hole is a death of deception, calm at first, only to betray you later. The black hole's size decides the manner of your end, but not the end itself. Both paths lead to dissolution. In this duality lies something almost philosophical. The stellar black hole offers honesty. You see your destruction before the horizon. You know the end as it comes. The supermassive black hole offers illusion. You believe you are still safe, even as the point of no return is behind you. Both are products of the same unyielding laws. Both reveal that safety is a human fiction, one that scale can extend, but never preserve. Einstein's theory of relativity sharpens this paradox further. To an outside observer, you appear to freeze at the horizon. In either case, they never see you destroyed. They see only your image dimming, stretched into red, fading into black. From their perspective, the violence never arrives. To you, the experience is unmistakable. In one case, agony strikes before the crossing. In the other, you pass the threshold unaware, only to face destruction later. Both realities exist at once, layered by perspective, reconciled by the geometry of space-time. This is the strange beauty of black holes. They do not simply destroy. They divide reality into perspectives. They reshape the meaning of distance and time. They force us to confront the relativity of truth. They are predators of matter, but they are also predators of certainty. They consume not only what falls into them, but also the idea of a single, objective narrative. And so, having traced the contrast between stellar and supermassive black holes, we arrive at a deeper question. What does it mean to fall, not only in space, but in time? What does it mean to be stretched, not only in body, but in perception? As spaghettification unfolds, time itself is distorted, light itself is bent, and the view of the universe becomes strange beyond imagination. To understand the full experience of this fall, we must go beyond size and scale. We must turn to the relativity of time and light. Falling into a black hole is not merely a journey through space. It is a journey through time itself, one that divides reality into two stories that never meet. The traveler and the observer see different universes. One plunges forward without pause, while the other seems to fade into eternity. Both are true, and both reveal the strange ways Einstein's relativity bends the fabric of experience. Imagine yourself once more approaching the abyss. For you, time feels as it always has. Seconds tick forward in your mind. Your heart beats, your thoughts move, your body struggles against the growing pull. Gravity stretches you into a thread, but the flow of time seems steady. There is no sense that the universe outside is rushing away. You are locked in your own personal rhythm, your own clock, and that clock refuses to betray you. But to the companion watching from afar, your clock does betray you. As you near the event horizon, signals from your body struggle against the pull. Each flash of light, each radio wave, each pulse of information climbs upward from a deeper pit in space-time. In climbing, it loses energy. Its wavelength stretches, redder and redder, weaker and weaker. The once bright figure of your body dims until it glows faintly, like a dying ember. Time for you has not slowed, but to them it has stretched nearly to a halt. They see you linger on the horizon, frozen. They will never see you fall inside. This is not illusion. It is the nature of space-time. Relativity teaches us that time and space are woven together, and that gravity curves this fabric. To you, inside your own frame, time flows normally. To them, outside, the curve stretches your signals into infinity. Both experiences are valid. Both are dictated by the same laws, and both coexist without contradiction. Reality itself allows for these dual stories. The strangeness deepens with light. Around the black hole, photons do not travel as they do in flat space. Paths bend, arcs curl, light loops around the horizon before either escaping outward or plunging inward. To your eyes, the universe distorts. Stars stretch into arcs. Constellations warp into rings. The sky itself bends into strange shapes. As you fall, more and more of the universe seems to cluster above you, bent by the pull. Looking upward, you might see the entire cosmos compressed into a shrinking dome of light, distorted and blue shifted by your motion. Looking downward, you see nothing at all, only blackness, where no light escapes. For the observer outside, the distortion is different. They see you elongated, stretched by the very process that destroys you. To them, your body becomes thinner, longer, fading into red, frozen at the edge. In truth, your body is already unraveling. The forces at your feet and head are no longer equal, and the stretching is real. But relativity ensures that your image, your final appearance to the outside world, is itself spaghettified. Your last photograph is one of distortion, stretched both physically and optically, a final ghostly line at the edge of darkness. This duality of vision and time is what makes black holes more than simple destroyers. They are laboratories of perspective. They remind us that the universe does not provide a single, shared narrative. To you, time continues. To others, you freeze. To you, the stars bend into strange arcs. To others, your body elongates and fades. Both stories are written into the geometry of the same fall. For the traveler, the view becomes stranger still as spaghettification progresses. Your body is stretched, but your vision is also warped. Light from behind curves around, so that the universe above seems to press in from every direction. You might see the past and future of the cosmos in accelerated sequence, stars burning out, galaxies colliding, the sky itself changing as if time outside were rushing forward. This is not fantasy, but relativity's decree. As you fall inward, your own time remains steady, while the rest of the universe seems to speed past. The truth is haunting. To fall into a black hole is to fall not only into space, but into another kind of time. It is to witness the universe outside in fast forward, while you yourself move toward an inevitable unraveling. Your body stretches into a filament. Your image stretches into red. Your perception stretches into a view of the cosmos racing ahead. Spaghettification is therefore not only a physical tearing, but also a tearing of perception, a distortion of what it means to move, to see, to exist. And so, as we explore this chapter, we will see how relativity reshapes every aspect of the fall. Time divides into two truths. Light bends into strange illusions. The image of the traveler and the experience of the traveler split apart forever. This is the spaghettified view, not just of the body, but of reality itself. To fall into a black hole is to fall into a fracture between perspectives. For you, time flows smoothly, unbroken, each second following the next, as it always has. Yet for the observer watching from far away, your time slows to a crawl, your movements dragging, your signals stretched thinner and weaker. The contradiction is only apparent. Relativity tells us both views are real, for time itself is not universal, but local, bound to the frame of the observer. Imagine looking upward as you descend. Above you is the entire cosmos, stars scattered across the vault of space, galaxies glowing faintly at impossible distances. But the closer you come to the horizon, the more distorted that vault becomes. Light does not travel in straight lines near a black hole. It curves, it loops, it bends. You see stars where they should not be, arcs of light circling around the dark core. In your final descent, the whole universe seems to gather above you, squeezed into a shrinking sky. And then comes the strangest illusion of all. As you fall, you look upward and witness the outside universe speeding ahead. Clocks in distant galaxies appear to race forward. Stars live and die in moments. Cosmic events unfold in quick succession. This is not because time has truly changed, but because your own frame of reference bends under the pull of gravity. The deeper you fall, the faster the rest of the universe seems to move. In your last moments, you may see billions of years unfold in the sky above. Meanwhile, the observer outside sees the opposite. To them, you slow as you approach the horizon. Your final gestures stretch across eternity. A wave of your hand takes years, centuries, millennia. Your signals, once bright, become fainter and redder until they vanish altogether. You seem to fade, to freeze, to merge with the horizon itself. The spaghettification that is tearing you apart is hidden from their eyes, replaced by an image of stillness and silence. To them, you are no longer a moving body, but a fading shadow. This divergence of experience is the essence of relativity. Time is not absolute, not the same for all. It flows differently depending on where you are, how you move, and what you feel. Falling into a black hole stretches this truth to its limits. It creates a world where one person can live seconds, while another sees them stretched across eternity. It is not illusion, not deception, but reality itself, divided by perspective. The bending of light reinforces the strangeness. If you had instruments to record the scene around you, you would find the universe warped almost beyond recognition. A star behind the black hole might appear in front of you, its light bent around the abyss. Rings of glowing arcs form, known as Einstein rings, where light from distant sources curves into perfect circles. The black hole does not only consume matter, it consumes geometry, twisting sight into patterns that no human eye has ever seen. And your own image, as recorded by an outside observer, suffers a final indignity. As you are stretched physically by tidal forces, your appearance is also stretched optically by relativity. To them, you become a line, a filament, a streak of dim red fading into darkness. Spaghettification is not only a process of matter, but a process of light. It is written both in what happens to you and in what happens to your image. Here lies a haunting symmetry. For you, the fall is immediate. The stretching of your body, the distortion of the sky, the rushing forward of the universe above all, are real. All are felt. For them, the outside observers, you are timeless. You do not fall. You only fade. Two truths, two perspectives, one reality. The black hole does not privilege one story over the other. It contains them both. This division between observer and traveler is what makes black holes not only objects of physics, but also objects of philosophy. They force us to ask, what is real? Is it what you feel in your final moments, the stretching, the distortion, the acceleration of the cosmos? Or is it what others see? Your body frozen, your light redshifted, your image never quite crossing the horizon. The answer, as relativity insists, is that both are real. Reality itself is layered, relative, perspectival, and still, beneath the strangeness of light and time, the physical truth marches on. Tidal forces continue to grow. Your body lengthens, narrows, unravels. Spaghettification advances step by step, indifferent to the distortions of perception. Whether seen or unseen, your fate is written into the geometry of space-time. The stretching of your body and the stretching of your image are twin expressions of the same law. This is the spaghettified view, a vision of a universe where time fractures, light bends, bodies stretch, and truth itself is divided. It is as much a phenomenon of perception as of destruction, as much about what is seen as about what is endured. To understand it fully is to see how relativity and gravity together weave a tapestry of horror and beauty, one in which the end of matter and the distortion of sight are inseparable. The final descent is not only a tearing of matter, but a distortion of vision. As you fall deeper, stretched and squeezed by tidal gravity, the universe above you becomes stranger still. The stars do not remain where they were. They arc, bend, and swirl around the dark void, their light curving along invisible paths written by space-time itself. The black hole becomes not merely a darkness, but a lens, gathering light from all directions, folding the sky into shapes the human mind was never meant to see. Looking upward, you would witness the cosmos itself accelerating. Galaxies shift, stars age and die, clusters collide. The background radiation of the universe cools and fades. What would take billions of years for those outside seems to you to unfold in moments. This is the consequence of relativity. Your own time flows steadily, but the time of the outside universe races ahead. In your final moments, you may glimpse the far future of the cosmos, a vision of ages you were never meant to see. For those who watch from a safe distance, your story is utterly different. They do not see you plunge through these transformations. They see only your image stretched, thinner, dimmer, redder. Your signals fade into silence. To them, you are frozen at the edge, a figure that never quite vanishes, but never continues. The light that carried your final gestures has been stretched beyond detection. For them, you linger on the horizon forever, a ghostly remainder of a journey they cannot share. This division between what is seen and what is lived is perhaps the most haunting part of falling into a black hole. For the traveler, the descent is real, immediate, relentless. For the observer, the descent is incomplete, suspended in eternity. Both stories are true. Both are written into the same fall. The universe does not force a choice between them. It accepts both as equally valid. The The culmination of this process is a kind of spaghettification of perception itself. Your body is stretched into a filament. Your image is stretched into a fading smear of red. Your time is stretched into eternity for those who watch. Even the light around you is stretched into strange arcs and rings. Everything elongates, bends, and distorts. Spaghettification is not only what happens to matter, but what happens to reality when pressed against the edge of extreme gravity. This strange duality reveals the full power of relativity. Einstein's equations were not only a new description of motion, but a revelation about the nature of truth. Time is not absolute. Space is not absolute. Even the order of events can differ between observers. Black holes amplify these principles until they become inescapable. They show us a universe where truth itself is relative, layered, perspectival, and where destruction and illusion are inseparable. And yet, within this cosmic strangeness, the end of the traveler is certain. No matter what illusions of time or light appear, the tidal forces do their work. Molecules split, atoms scatter, matter stretches into a filament. The black hole accepts no exception. It consumes all equally, whether star, planet, or human. Relativity may split the story into two versions, but both lead to the same conclusion. The horizon is past. The body unravels. The thread of matter vanishes into the dark. It is this combination of physics and perception that makes spaghettification not only a scientific phenomenon, but also an existential one. It is death not only by gravity, but by perspective. A reminder that what we call reality depends on where we stand. To the traveler, there is falling and stretching. To the observer, there is fading and freezing. Both are true. Both end in silence. And so Chapter 5 draws to its close. We have seen how time divides, how light bends, how vision and truth themselves are stretched by the fall. We have followed the traveler as the universe above accelerates and the stars bend into strange rings. We have followed the observer as they watch a figure fade into eternity. Together, these stories form the spaghettified view, a vision of reality distorted by gravity's greatest grip. Ahead lies evidence that this is not mere theory. Astronomers have seen stars torn apart by these same forces. They have recorded the flares of light, the jets of energy, the debris of suns, shredded by invisible predators. The cosmos has already shown us spaghettification on scales vast beyond imagination. In the next chapter, we turn to these tidal disruption events, the cosmic signatures of matter being unraveled, and we will see how the death of stars reveals the truth of what would happen to us. The universe has already shown us what happens when spaghettification strikes. We do not need to imagine it only as theory or as the fate of an unlucky traveler. Astronomers have watched entire stars torn apart by black holes. These are called tidal disruption events, and they are among the most dramatic spectacles in the cosmos. Picture a star wandering too close to the dark heart of a galaxy. For billions of years, it has burned quietly, its light shining across space, its gravity balanced against the fusion at its core. But on its fateful orbit, it drifts too near to the invisible giant at the galaxy's center. The star crosses a distance where the gradient of gravity across its body becomes fatal. Its near side feels a stronger pull than its far side. The difference is immense. In moments, the star is no longer a sphere of plasma, but a stream of gas, stretched, elongated, broken apart by tides that do not care what it once was. What follows is a cosmic spectacle. The shredded star's gas does not vanish at once. It swirls into a disk around the black hole, heated to temperatures of millions of degrees. The disk glows across the spectrum, releasing bursts of light so powerful they outshine entire galaxies. Some of the star's material is consumed, falling forever inside. Some is flung outward, escaping at nearly the speed of light in jets that pierce the surrounding space. The star has been destroyed, but in its destruction, it lights the sky with one final blaze. Astronomers have given names to these events. They are rare, but they leave signatures we can detect across millions or billions of light years. In the year 2014, telescopes caught sight of one such flare in a galaxy hundreds of millions of light years away. It was labeled ASASSN 14Li, short for All Sky Automated Survey for Supernovae. The flare brightened quickly, then faded over months, a clear sign that a star had been torn apart and devoured by a supermassive black hole. Such discoveries are not isolated. Over the past decades, observatories have found dozens of these events. Each one confirms the predictions of physics. Stars do not simply vanish when they meet black holes. They unravel. They stretch into filaments of gas. They ignite one last time as their remains swirl in furious disks. These are spaghettifications written on a stellar scale, cosmic autopsies recorded in light. The beauty of tidal disruption events is that they reveal black holes not by what they are, but by what they do. A black hole itself cannot be seen. It emits no light. It reflects nothing. But when a star is caught in its grasp, the evidence blazes across the universe. We see the flare of its death. We measure the spectrum of its heated gas. We trace the jets that erupt from its poles. The invisible predator reveals itself only in the violence it inflicts. For scientists, these events are not only confirmations of theory, but also tools of discovery. By studying the flares, we learn the masses of the hidden black holes, their spins, their hunger. Some events even allow us to measure the flow of matter in exquisite detail, confirming predictions made by Einstein's relativity and by modern astrophysics. Each tidal disruption event is a laboratory of extremes, a chance to see spaghettification on scales far beyond human experience. And yet, even as we marvel at these cosmic fireworks, there is a sobering thought. If gravity can do this to stars, what chance would a human body have? If entire suns are unraveled into ribbons of plasma, then flesh and bone would be dust in an instant. The same process that lights galaxies with stellar death would make the destruction of a traveler almost unnoticeable. Against the scale of the cosmos, the human form is fragile beyond measure. These stellar deaths are therefore more than scientific curiosities. They are warnings written across the sky, reminders that spaghettification is not a metaphor, but a fact. The same forces that shred stars will shred anything that dares to cross the critical distance. Whether a sun, a planet, or a person, the outcome is the same. The universe has shown us the evidence. The stories are not fantasy. They are written in the light of flares we have already seen. And so, in the first part of this chapter, we see spaghettification not as imagination, but as fact. Stars wander too close, and they are destroyed. In the parts ahead, we will dive deeper into the details of these tidal disruption events, into the case studies of stars that have been shredded, and into the ways astronomers have confirmed the predictions of theory. In their deaths, we find proof of what awaits any matter, no matter its scale, when it crosses too close to gravity's darkest grip. The story of spaghettification is not confined to the realm of theory. In the last decades, astronomers have witnessed the process unfolding in real time. Each tidal disruption event is like a signature, a cosmic crime scene where the victim is a star and the perpetrator is a black hole. The light that reaches our telescopes carries the evidence, and from that evidence, we reconstruct the final moments of suns that dared to venture too close. Among the most famous of these events is the one known as ASASSN 14Li. It was first noticed in November of the year 2014 by the All Sky Automated Survey for Supernovae, a network of small telescopes scanning the heavens for sudden outbursts. What they saw was not the birth of a supernova, but the death of a star. In a galaxy hundreds of millions of light years away, a sun like our own had strayed into the reach of a supermassive black hole. Its fate was sealed. Over the months that followed, ASASSN 14Li was studied by some of the most powerful observatories on Earth and in orbit. X-ray telescopes revealed high-energy emissions from the gas swirling into the black hole. Optical telescopes tracked the fading light as the remains of the star cooled. Radio telescopes traced the jets of material ejected at nearly the speed of light. Piece by piece, the evidence built a complete picture. A star stretched into ribbons, heated, shredded, and partly consumed. The spaghettification of a sun had been caught in the act. Other events have since joined the record. In 2019, astronomers detected AT2019 Kies, a tidal disruption event in a galaxy only about 215 million light-years away, close enough to allow unprecedented detail. It became known as the Rosetta Stone of tidal disruptions. Observations showed how the star's material first formed streams, then circled into a disk, then shone as it spiraled inward. For the first time, scientists could watch the stages of spaghettification unfold, almost step by step. There are other names and other victims. Swift J1644+57, an event that produced jets so powerful they could be seen across the universe. XMMSL 14J0619, where the flare of a shredded star lit up a quiet galaxy. Dozens more captured in surveys that scan the skies night after night. Each case is a variation on the same theme. A star wanders too near, the tides take hold, and in weeks or months, it is no longer a star, but a smear of gas around a hidden singularity. The details vary with each event. Sometimes the star is completely destroyed, all its matter falling into the black hole or being flung outward. Sometimes only part of the star is stripped, and what remains continues to orbit, scarred, but alive, destined to return for another encounter. In either case, the lesson is the same. Tidal forces are merciless. They can tear suns into filaments as easily as waves can scatter foam. For astronomers, these events are more than cosmic curiosities. They are natural experiments, allowing us to test theories that cannot be reproduced in any laboratory. By measuring the light curves, we confirm how matter heats and cools under extreme gravity. By tracing the jets, we test our understanding of how magnetic fields interact with disks of plasma. By mapping the spectra, we learn about the chemical composition of stars as they are dismantled. In every case, observation aligns with prediction, confirming that the spaghettification of stars is not speculation, but fact. The most haunting aspect is the timescale. For the star, the destruction may unfold in hours or days. For us, watching from Earth, the light may take hundreds of millions of years to arrive. The flare we see tonight may be the echo of a star that was destroyed long before humanity even existed. Each tidal disruption event is both immediate and ancient, its evidence traveling across the abyss of time before reaching our telescopes. The destruction of stars in this way also reminds us of our place in the cosmos. The sun of our own system is safe, too far from any black hole to risk such a fate. Yet the fact that other suns have been undone tells us what the universe is capable of. If a body as massive and enduring as a star can be shredded into filaments of plasma, then what hope would there be for us? If gravity can erase the identity of a sun, then the unraveling of a human body would be barely a whisper in the darkness. Tidal disruption events are cosmic warnings. They tell us that spaghettification is not a poetic metaphor, not an abstract concept, but a real force that shapes galaxies. They show us what happens when the balance of fusion and gravity that keeps a star alive is broken by an even stronger gravity. They confirm that destruction, by stretching, is not confined to imagination. It is written into the light of flares we can see with our own eyes. And so, with each new detection, the evidence grows. The universe itself demonstrates spaghettification on scales we can measure. In the next part, we will examine what these stellar deaths mean, not only for astronomy, but for philosophy. For if stars can be unraveled, thread by thread, then so can we. The difference is only one of scale. The universe has been our witness. Through the eyes of telescopes, We have seen what happens when stars fall into the reach of black holes. Each tidal disruption event is a cosmic testimony that spaghettification is not speculation, but reality, written not in equations alone, but in light itself. The patterns are unmistakable. A star strays too close, its sphere distorted, its symmetry broken. The side nearest the black hole accelerates faster than the far side, and the difference grows until the star can no longer hold together. It is stretched into a stream, a ribbon of plasma pouring into orbit. Some of the stream circles to form a glowing disk, spiraling inward in a frenzy of heat and light. Some of it is flung outward, scattered across space, never to return. What was once a singular body, self-contained and balanced, becomes a filament spread across millions of kilometers. These cosmic flares, brief on astronomical timescales, are visible across billions of light years. They are among the brightest events the universe can offer, outshining entire galaxies for weeks or months. To human instruments, they are a blaze of X-rays, ultraviolet light, visible light, and radio waves. To human imagination, they are the death cries of stars, the proof that even suns cannot escape the sculpting power of tides. The evidence has grown clearer with each passing decade. In the 1980s, the first candidate events were glimpsed, flares that could not be explained as supernovae. In the 1990s, space telescopes revealed more. By the 21st century, dedicated surveys were capturing them regularly. Today, they are expected, catalogued, studied in detail. They are not anomalies, but chapters in the story of galaxies. Every galaxy with a supermassive black hole is capable of such violence, and many have already displayed it. Astronomers treat these events as both confirmations and puzzles. They confirm the basic physics of spaghettification, the stretching of matter under tidal gravity. They confirm Einstein's predictions of how energy is released near horizons. But they also raise new questions. Why do some events produce powerful jets while others remain quiet? Why do some disks shine brilliantly while others fade quickly? What roles do magnetic fields and spin play? Each tidal disruption event is a laboratory, a natural experiment, a chance to refine our understanding of the deepest laws of nature. For those outside the halls of science, the meaning is more visceral. A tidal disruption event is proof that gravity can unmake even the most massive and enduring structures in the universe. A star, sustained for billions of years by the furnace of fusion, undone in weeks by the difference in pull across its surface. This is the same principle that raises Earth's tides, extended to its most extreme conclusion. The same geometry that moves oceans also destroys suns. And here, the imagination turns inward. If gravity can do this to stars, what chance does a human body have? Flesh and bone are fragile beyond measure compared to stellar plasma. The scales are different, but the process is the same. A body crossing the critical distance would be stretched, squeezed, and unraveled, just as surely as a star. The cosmos has shown us the large-scale version. The small-scale fate is inevitable. There is a chilling symmetry in this. Tidal disruption events show us spaghettification as both spectacle and warning. They remind us that matter is not safe simply because it has coherence. Identity, whether of a star or a body, is only temporary in the face of absolute gradients. Structure is fragile. Gravity is patient. In time, every form yields. And so the story of spaghettification moves from the cosmic to the personal. We have watched stars fall and be undone. Now we must imagine ourselves in their place. What happens to the human body as it meets the same fate? What would it feel like to be stretched, compressed, and unraveled thread by thread? The next chapter narrows the scale from suns to flesh, from galaxies to the human form, and asks the most intimate question of all: what is it like to be spaghettified? The cosmos has already shown us what happens to stars, but to bring the story closer, we must imagine what it would mean for a human being to face the same fate. Though our bodies are infinitely smaller and more fragile than suns, the principle is the same. Gravity does not discriminate. The same tidal forces that shred stars into streams of gas will, on a vastly smaller scale, dismantle flesh, bone, and even the bonds of molecules. Spaghettification is impartial, and to imagine it step by step is to confront both the science and the horror of our own fragility. Picture yourself approaching a stellar mass black hole, drifting downward feet first. At first, nothing unusual occurs. You feel the steady pull, as any astronaut would in free fall. There is no sensation of weight, no resistance. But as you approach closer, the difference in pull between your feet and your head becomes noticeable. Your legs are drawn downwards slightly faster than your chest. Your chest is pulled faster than your head. The difference is small at first, a discomfort, like an invisible stretch along your spine, but it grows steadily, relentlessly, doubling with every moment. Your body begins to lengthen. Muscles tighten as they try to resist, but the resistance is futile. The stretching comes not from outside, but from space itself. The geometry of space-time is dictating the path of each part of your body. It is not a force you can brace against, or an impact you can withstand. It is the very shape of reality, pulling you apart. Soon the strain exceeds what muscles and tendons can bear. Fibers tear. Joints separate. Bones, rigid though they are, begin to snap under the differential pull. The skeleton that gives you shape becomes a chain of fragments, each link pulled along its own curve. You are no longer a single structure, but a lengthening filament. At the same time, you are squeezed from side to side. Tidal gravity stretches along one axis, but compresses along the others. Your chest narrows, your arms press inward, your body thins, even as it elongates. This dual effect of stretching and squeezing is the essence of spaghettification. You are becoming a thread, long and narrow, drawn into the shape of the geometry itself. As the process deepens, organs rupture, blood vessels tear. The body that once coordinated its systems into life becomes a cascade of parts. Consciousness would not survive long. Pain would come first, then disorientation as oxygen fails to reach the brain, then blackout. From a human perspective, death occurs quickly, long before the final unraveling. But the process itself continues. Molecules are the next to fail. The chemical bonds that hold atoms together in proteins, lipids, and DNA cannot endure the differential pull. They break apart, leaving streams of atoms. Atoms themselves, bound by electromagnetic force, may survive longer, but even these are not immune. The gradient of gravity grows so intense that even electrons are stripped from nuclei. Plasma replaces flesh. What was once a human body is now a thread of elementary particles, falling inward, stretched along the path of geometry. From the outside, none of this is seen. To observers, you never cross the horizon. Your body appears to freeze, dim, fade. The spaghettification that dismantles you atom by atom is invisible to their eyes. For them, you remain at the edge, an image never completed. For you, the destruction is total, each layer of structure undone in turn. The impartiality of the process is what makes it terrifying. There is no point at which the body can resist. Muscles cannot, bones cannot, molecules cannot, even atoms cannot endure indefinitely. The same laws that stretch oceans into tides and stars into streams will dismantle a human form completely. Scale is the only difference. The principle is the same. And so the first stage of imagining the human fate is clear. Spaghettification begins with a gentle stretch and ends with the dissolution of structure itself. Death comes quickly, but the process does not stop. Flesh, bone, molecules, atoms, all yield to geometry. To fall into a black hole is not only to die, but to be unmade, thread by thread, until nothing remains but a stream of matter, lost to the abyss. The unraveling of the human body under spaghettification can be traced layer by layer, a grim dissection, not by scalpel, but by gravity itself. It begins with a stretch that seems harmless, a gentle elongation you might imagine from a carnival mirror. But as you approach closer to the black hole, the difference in pull between one end of your body and the other grows at an exponential rate. Within seconds, the tension becomes catastrophic. The skeleton is the first to betray you. Your bones are strong under compression, but weak against the shearing of differential gravity. The vertebrae of your spine are pulled apart. Joints pop, ligaments snap. Your legs elongate, like strands of rope being tugged from both ends. The pelvis cracks as one half is dragged faster than the other. Ribs stretch outward before collapsing inward under the sideways squeeze. The architecture that supports you, painstakingly evolved for Earth's gentle gravity, shatters like brittle glass in the furnace of tidal strain. As bones yield, the body's soft tissues follow. Muscles tear as fibers are stretched beyond their limits. Tendons peel apart, no longer binding joints. Blood vessels elongate until they burst, releasing streams of fluid that themselves are drawn into filaments. The heart, compressed laterally and stretched vertically, ceases its rhythm. The lungs are squeezed thin, air escaping in an unvoiced scream. Every organ is distorted, transformed from a compact structure into a grotesque extension along the axis of the fall. Even as death has already claimed consciousness, the body's fate continues to unfold with mechanical precision. Gravity is not merciful. It does not stop when life ends. It continues, breaking down every level of structure. Proteins unravel as the bonds between amino acids snap. Cell membranes rupture, their complex architecture dissolved by tension. DNA itself, the molecule that encodes the instructions of life, is pulled into fragments. Each spiral of the double helix, painstakingly coiled and folded, is torn into pieces. Still, the process deepens further. Atoms, those indivisible foundations of matter, seem indestructible to us. Yet, even they are not immune. The gradient in gravitational pull grows so extreme that electrons are stripped from nuclei. Hydrogen, carbon, oxygen, the elements of life, are ionized, converted into plasma. What was once the chemistry of biology becomes a river of naked particles. The plasma, too, is not safe. As the stream falls deeper, protons and neutrons are forced along different trajectories, their bonds strained. At the very edge, even these particles may unravel, their quarks exposed to forces we can only speculate about. The laws of physics themselves, as we know them, begin to falter under such extremes. The body is no longer a body, no longer atoms, no longer matter as we recognize it. It has become a thread of fundamental particles, lost to the darkness. From the perspective of the falling traveler, much of this is beyond perception. Consciousness would fade long before molecules or atoms are dismantled. But to imagine the sequence is to see the absolute nature of spaghettification. It is not merely death, it is disassembly, an erasure of identity written into the structure of space-time itself. No trace of the original form remains. From the perspective of the observer outside, none of this destruction is visible. They see only a frozen image, stretched across the horizon, dimmer with each passing moment. To them, the person is not torn apart, but held forever at the edge, a fading smear of red light that never crosses into darkness. The truth is divided. One version witnesses dissolution, the other sees only suspension. Both are dictated by relativity, and both are real. In this way, spaghettification is more than the end of a body. It is the stripping away of structure itself, step by step, until matter is unmade. It is the great equalizer, reducing the complexity of life into streams of particles indistinguishable from the debris of stars. A human being, a planet, a sun, all yield to the same geometry. All are drawn into threads that vanish beyond the horizon. And so, as we follow this step-by-step unraveling, we are forced to confront an unsettling truth. Spaghettification is not just destruction. It is erasure. It is the loss of not only life, but of form, of coherence, of meaning written into matter. In the final part of this chapter, we will see the last stage of the journey, the surrender of what remains into the accretion disk, the final recycling of the body's essence into the cosmos itself. The final stage of spaghettification is not only the destruction of structure, but the dispersal of what remains into the machinery of the black hole itself. After bones have cracked, organs ruptured, molecules broken, and atoms stripped, the debris of the human form continues its fall. It does not vanish instantly. It becomes part of a stream of matter spiraling toward the horizon, joining other particles in a last chaotic dance before the silence of the interior. This stream of debris is stretched into an ever thinner filament, drawn into the black hole's surrounding disk if one is present. The accretion disk is a furnace of unimaginable energy, a whirlpool of gas heated to millions of degrees as it races inward at near the speed of light. The remnants of the body are swept into this disk, colliding with other particles, heated, ionized, transformed into radiation. What once was flesh now becomes light, shining across the cosmos for a brief moment before being consumed. Some fraction of the matter may not fall directly inward. Magnetic fields tangled in the disk can fling particles outward in narrow beams called relativistic jets. These jets pierce space with streams of energy that travel for thousands of light years. A small portion of what you once were could, in theory, be accelerated outward at nearly the speed of light, joining the intergalactic medium, scattered into the darkness between galaxies. A fragment of your existence could escape in the form of pure radiation, yet the bulk of the body's matter obeys gravity's command. It crosses the horizon, carried inward on a path no force can resist. From that moment on, it is cut off from the outside universe. No light, no signal, no particle can carry its story outward. The matter becomes part of the black hole's mass, contributing to its gravity, its spin, its charge. In the most literal sense, you are absorbed, your identity reduced to a handful of numbers that describe the black hole's state. This is the ultimate erasure. The complexity of life, the pattern of molecules, the organization of cells, the memory of thoughts, all are gone. Only mass, momentum, and charge remain, folded into the anonymous bulk of the black hole. The individuality of matter is stripped away. The universe keeps only the simplest ledger: how much, how fast, what sign. Yet even here, in this bleak finality, there is continuity. The matter that becomes part of a black hole is not lost to existence itself. It continues to curve space-time, to shape the orbits of stars, to bend the paths of light. If a black hole eventually evaporates through the slow radiation predicted by Hawking, then particles may one day emerge again, scattered back into the cosmos. In that distant epoch, fragments of what fell in may rejoin the universe in a form unrecognizable but real. The recycling of matter in this way links spaghettification to a broader cosmic story. Stars are born, live, and die, seeding space with heavy elements. Planets form, life arises, bodies exist. When gravity pulls those bodies into black holes, they are unmade, but their essence contributes to the energy and structure of the cosmos. Spaghettification, though terrifying, is also part of the cycle of matter, the endless reworking of the universe. From the perspective of human imagination, this offers both horror and consolation. Horror, because the process is absolute, reducing the body to nothing but a thread of particles swallowed by the abyss. Consolation, because those particles are not annihilated, only transformed, their existence carried forward in new forms, their essence written into the continuing story of the universe. And so the chapter closes with this vision: a body stretched, torn, dismantled, and absorbed, yet also recycled, reworked, redistributed. Spaghettification is the end of individuality, but not of matter itself. What was once a human being becomes part of the energy of the black hole, perhaps someday radiated back into space, scattered into the interstellar void, and in time reborn into new stars. The journey from flesh to filament, from body to radiation, is a reminder of both fragility and continuity. Spaghettification is the most intimate form of cosmic death, yet it is also part of the same cycle that builds galaxies. In the next chapter, we will explore this paradox more fully, confronting the horror and the beauty of spaghettification, and asking why it captivates our imagination as much as it terrifies. There is a reason the idea of spaghettification seizes the imagination. It is not simply another way of dying, nor merely an outcome of physics. It is something more, something that touches a deeper nerve in us. It combines terror with wonder, science with myth, the brutality of destruction with the elegance of natural law. In the black hole's embrace, we find both the most horrifying fate imaginable and one of the most profound expressions of the universe's beauty. To begin with the horror, spaghettification is death at its most absolute. It is not merely the cessation of life, as with illness or old age. It is the dismantling of the body, the erasure of identity, the undoing of matter itself. Flesh, bone, molecule, atom, all are torn apart, until what remains is no longer recognizable as a person. This frightens us because it confronts us with the total loss of self. There is no intact body to bury, no remnant to hold, no trace that remains distinct. The black hole accepts everything and leaves behind nothing but numbers describing mass and spin. It is annihilation stripped of sentiment, a fate that denies memory or legacy. And yet, woven into that horror is beauty. Spaghettification is not random chaos, but the perfect consequence of natural law. Gravity stretches and squeezes in precise directions. The mathematics of relativity explains exactly how the process unfolds. The universe is not cruel for cruelty's sake. It is consistent, elegant, indifferent. The very equations that describe the tides on Earth's oceans also describe the shredding of stars and bodies near black holes. What terrifies us is also what makes the cosmos intelligible. The beauty deepens when we consider the broader cycle. The matter consumed by a black hole is not lost to existence. It adds to the mass of the abyss. It contributes to the curvature of space-time. It may one day re-emerge through the slow whisper of Hawking radiation. Even the most violent endings become part of a larger process. The star that dies in a tidal disruption event lights up its galaxy one last time, seeding the cosmos with energy. The person who is unraveled into particles becomes part of the great balance of matter. Horror becomes transformation, and transformation becomes a kind of continuity. Perhaps this is why spaghettification fascinates as much as it terrifies. It is not just destruction, but revelation. It reveals the power of gravity to shape not only orbits, but existence itself. It reveals relativity's truth, that time and perspective are fractured, that reality can contain two contradictory stories at once. It reveals the fragility of life and the permanence of matter. It shows us that our fears and our wonder are two sides of the same coin. The idea also resonates with something ancient in us. To be swallowed by a black hole is to be devoured by the universe itself, to be claimed by something far larger than ourselves. In myths, monsters consumed heroes whole, dragons swallowed knights, cosmic beasts ate worlds. The black hole is the modern incarnation of those myths, but with the authority of physics behind it. It is the devourer made real, and spaghettification is its method. The fear it evokes is not new. It is the fear of being absorbed by something vast and indifferent, dressed now in the language of relativity. Yet where myths end in terror alone, spaghettification carries beauty in its wake. The destruction of matter creates luminous flares, arcs of light, distortions of the sky. To fall into a black hole is to see the universe in a way no one else can, to witness galaxies bending into rings, to watch time accelerate into eternity. Even as it destroys, Gravity creates visions of unparalleled grandeur. There is poetry in the way horror becomes wonder, in the way annihilation reveals the structure of the cosmos. And so, in contemplating spaghettification, we stand at the border of two truths. It is the most frightening fate we can imagine, and also one of the most awe-inspiring. It horrifies us because it unravels identity. It captivates us because it displays the laws of nature in their purest form. In this paradox lies the full meaning of spaghettification. It is not only a physical process, but an encounter with the sublime, where terror and beauty meet in the same falling thread. The horror of spaghettification comes not only from the destruction itself, but from what it represents. To imagine yourself falling into a black hole is to imagine the universe itself as predator. There is no escape, no bargain, no reprieve. The force is silent, invisible, and absolute. It does not chase its prey, for it does not need to. Anything that crosses the fatal distance is claimed, stretched, and consumed. The black hole is the patient hunter, waiting at the heart of galaxies for eons, devouring suns, and scattering the ashes of their remains. This image strikes a chord in human imagination, because it evokes our oldest fears. In myths and stories from every culture, there are monsters that devour, serpents that coil around the world, creatures that swallow the unwary whole. The black hole is their scientific heir, and spaghettification is its method of consumption. But unlike myth, this monster is real. We have seen its signs in the flares of shredded stars, in the jets piercing space, in the bending of light itself. To know that such a devourer exists is to feel the echo of those ancient fears, magnified by the cold indifference of physics. The dread deepens when we realize how absolute this process is. Many dangers can be resisted, fire can be quenched, storms can be sheltered from, predators can be fought or fled. But gravity at the scale of a black hole offers no defense. It is not a force we can shield against or outrun. Once the horizon is crossed, the story is over. The spaghettification of the body is not a possibility, but a certainty. It is the inevitability that frightens us most. Yet, even in this inevitability, there is beauty. The black hole does not devour in darkness alone. It lights the cosmos with the death of its victims. The radiation from accretion disks, the arcs of bent light, the jets that streak across galaxies. These are displays of grandeur that exist only because matter has been unmade. The destruction creates spectacle. Horror and wonder are bound together, inseparable, two faces of the same event. For the falling traveler, the terror lies in the experience itself. To feel the body stretched, the chest compressed, the vision distorted, the stars racing ahead, this is cosmic horror written in physical sensation. For the observer outside, the horror lies in the silence. They see the traveler freeze, fade, and vanish, unable to cross the edge, unable to return a signal. Both perspectives capture different aspects of dread, yet both are true. Spaghettification terrifies because it denies not only survival, but communication. It severs connection, isolates the victim absolutely, and then erases them. And still, the beauty persists. Consider the geometry itself. The equations of Einstein describe precisely how space-time bends, how matter falls, how light curves. The mathematics is elegant, a lattice of logic that unfolds into predictions later confirmed by observation. There is artistry in these equations, as if the cosmos itself is written in patterns of extraordinary coherence. Spaghettification is terrible, but it is terrible with precision. It is horror, guided by elegance. The paradox is inescapable. The same process that obliterates individuality also creates visions of unmatched grandeur. The same predator that consumes suns also sculpts galaxies with its pull. The same fate that terrifies us also inspires us to study, to imagine, to create art and story. Horror and beauty are not opposites here. They are the same phenomenon, seen through different eyes. This is why spaghettification has taken root in our imagination as more than just a scientific curiosity. It is the perfect fusion of cosmic horror and cosmic beauty. It reminds us of our fragility, while showing us the majesty of the laws that govern everything. It denies us comfort while offering us awe. It tells us that the universe is both predator and artist, both destroyer and creator, both indifferent and magnificent. And so, as we linger in the second part of this chapter, we come to see why spaghettification resonates so deeply. It is not merely that it kills, it is that it does so in a way that strips away illusion. It shows us what it means to live in a universe where even time, light, and matter can be unmade. It frightens us because it reveals that truth. It captivates us because the revelation is so profoundly beautiful. The more we dwell on spaghettification, the more its dual nature emerges. It is, at first glance, the most dreadful fate imaginable. To be stretched and broken until all structure is erased is annihilation in the purest sense. Yet when we step back, when we look not only at the victim but at the larger picture, we find that spaghettification is also a profound part of the cosmic cycle, a process that binds us to the stars and to the universe itself. For what is destroyed is not lost. Matter pulled into a black hole does not vanish into nothingness. It is transformed, incorporated, its mass added to the black hole, its energy radiated in the heat of the accretion disk, its fragments perhaps scattered outward in jets of light and plasma. The individuality of the body, the coherence of the star, the identity of the object, these are erased. But the essence, the raw matter and energy, persists. It continues to shape space-time, continues to influence the cosmos, continues to exist, even if in forms that bear no resemblance to what they once were. Here lies the beauty, hidden within the horror. Spaghettification is not only an end, it is a beginning of another kind, a recycling of matter into the larger system of the universe. The star that is destroyed becomes part of the black hole's mass, but also part of the galaxy's story. The traveler who is shredded becomes part of the abyss, but also, perhaps, part of the radiation that may one day escape. The individual is erased, but the universe endures, reshaped and rebalanced by every act of destruction. For humanity, this is both humbling and strangely comforting. It reminds us that our fear of death, our clinging to identity, is small compared to the vast cycles of the cosmos. We fear the erasure of self, but physics tells us that even in erasure, there is continuity. The building blocks remain, carried forward, reshaped into new patterns, new stars, new galaxies. To be spaghettified is to lose everything we know as self, but it is also to rejoin the matter of the universe in its eternal dance. This is why spaghettification captivates us so deeply. It is not only destruction, it is destruction fused with meaning. It is horror interwoven with beauty. It is the cosmic predator devouring its prey, and it is the artist painting with light and gravity. It is the myth of annihilation and the truth of transformation, bound together in one process. We are terrified because it strips us away, but we are fascinated because it reveals the universe in its rawest form. There is also a philosophical dimension that cannot be ignored. To face spaghettification is to face the indifference of the cosmos. The universe does not care for our fears, our hopes, our memories. It obeys its laws without sentiment. And yet, in that very indifference, there is majesty. The laws are consistent, beautiful, unyielding. They reveal that we live not in chaos, but in a cosmos governed by patterns of deep coherence. Even in our destruction, we are participants in that order. Thus, spaghettification is not just a death by gravity. It is a mirror held up to the nature of existence. It forces us to confront the limits of individuality and the continuity of matter. It horrifies us because it denies us permanence. It awes us because it shows us the elegance of the universe's design. It fascinates us because it speaks to the oldest fears and the deepest questions of what it means to exist. As this chapter closes, we stand at the edge of physics and philosophy. We have seen how spaghettification terrifies us with its brutality and captivates us with its grandeur. We have seen how it erases structure yet preserves essence, how it destroys individuality, yet contributes to continuity. But there is still a deeper puzzle that spaghettification raises. If matter is unraveled and swallowed, what happens to the information it carried? Can the universe truly erase information, or must it be preserved in some hidden form? This question leads us into one of the greatest mysteries in science, the black hole information paradox. And so, the story continues. From the horror and beauty of spaghettification, we move to the paradoxes it reveals, where quantum mechanics and relativity clash, where physics itself reaches its limits, and where the fate of information becomes as mysterious as the fate of matter. To understand spaghettification fully, we must go beyond the tearing of matter and ask a deeper question: what happens to the information encoded in what is destroyed? A star shredded by tidal forces carries within it the record of its mass, its elements, its history of nuclear burning. A human body carries not only the atoms that compose it, but the arrangement of those atoms, the structure of proteins, the sequence of DNA, the patterns of electrical activity in the brain that form memories. When such a body or star is pulled across the horizon of a black hole, we must ask, does that information vanish forever, or is it somehow preserved? This question is not just philosophical, it cuts to the heart of physics itself. In classical relativity, the answer seems clear. Once matter crosses the event horizon, it is gone from the universe. No signal can emerge, no particle can return, no record can be retrieved. To the outside world, the information is lost. The black hole becomes a simple object, described only by three numbers: its mass, its spin, and its electric charge. This is the no-hair theorem of black holes. They have no distinguishing features beyond these values. Two black holes of identical mass, spin, and charge are indistinguishable, no matter what different histories produced them. All individuality is erased. But quantum mechanics rebels against this conclusion. In the quantum world, information is sacred. The laws of physics do not allow it to be destroyed. Even when particles decay, even when systems transform, the total information is preserved, encoded in new arrangements. If black holes truly erased information, they would break the most fundamental principle of quantum theory. This conflict between relativity's prediction of loss and quantum theory's insistence on preservation is known as the black hole information paradox. The paradox sharpens when we consider Hawking radiation, the slow emission of particles that allows black holes to evaporate over immense timescales. Stephen Hawking showed in the 1970s that black holes are not perfectly black. They emit radiation due to quantum effects near the horizon, pairs of particles separating, with one falling in and the other escaping. Over trillions of years, a black hole can evaporate completely. But if this is true, what happens to the information inside? If the black hole disappears, does the information vanish with it? That would break the laws of quantum mechanics. And yet, relativity offers no path for the information to escape. Here, spaghettification becomes part of the puzzle. The body falling in is not only matter, but information encoded in structure. As it is stretched and torn, that information is scattered, scrambled, seemingly lost. But physics demands an accounting. Some theorists suggest that the information is imprinted on the event horizon itself, stored like a hologram on its surface. This idea, known as the holographic principle, suggests that everything that falls into a black hole leaves its mark on the horizon in two-dimensional form, even as it appears to vanish in three dimensions. Others propose that information leaks out with Hawking radiation, hidden in correlations so subtle we cannot yet detect them. Still others have proposed more radical solutions. One is the idea of the firewall, that the horizon is not smooth, but a searing boundary that burns anything that falls in, releasing information at the edge, rather than allowing it to cross. Another is that space-time itself is woven holographically, with the interior of the black hole existing only as a projection of information encoded at the boundary. In these views, spaghettification is not only a physical destruction, but also part of the mechanism by which the universe preserves its information, even if in ways we cannot yet comprehend. This tension between destruction and preservation echoes the paradox of spaghettification itself. The body is shredded, yes, but is the information of that body truly erased? Or is it preserved in some hidden way, encoded in the black hole's surface, carried outward in faint radiation, or stored in the geometry of space-time itself? Science does not yet know the answer. What we do know is that the paradox remains one of the deepest mysteries in physics, a riddle that may point the way toward a theory unifying quantum mechanics and relativity. And so spaghettification, which begins as a vivid physical process of stretching and tearing, leads us to the frontiers of science. It is not only the death of matter, but the test of theory. It forces us to confront questions of permanence and erasure, of what it means for information to exist, of whether the universe itself allows true loss. Perhaps one day, when quantum gravity is fully understood, we will learn that nothing is ever truly destroyed, that even in the abyss of a black hole, the threads of identity remain woven into the cosmos. Or perhaps we will learn that loss is real, that some stories truly end without remainder. Until then, spaghettification stands as both a physical fate and a philosophical challenge. It destroys bodies, but also challenges laws. It tears apart matter, but also pulls together the deepest questions of physics. It reminds us that to fall into a black hole is not only to vanish, but to press against the limits of what science can describe. And as we near the final descent of this journey, we carry these questions with us. Spaghettification is not only about death by gravity, it is about the paradox of existence itself, the confrontation between what we know and what we cannot yet explain. In the next and final chapter, we will bring together the strands of this story, reflecting on what spaghettification tells us, not only about the universe, but about ourselves, and why this ultimate fate is a reminder of both our fragility and our connection to the cosmos. The journey ends as it began, with gravity, from the tides of Earth to the stretching of stars, from the unraveling of flesh to the paradoxes of information. Spaghettification has guided us into the deepest shadows of physics and philosophy. Now, at the end, we descend once more, gathering the strands into a single thread, much like the bodies and stars that fall into black holes. This is the final descent, where science and story merge, where terror and beauty unite, where the cosmos reveals itself in its most uncompromising form. Imagine again the traveler approaching the abyss. At first, the fall feels ordinary. Gravity pulls, as it always has, invisible and patient. There is no sudden rupture, no sharp edge in space-time. The descent is silent, smooth, inevitable. Yet every moment deepens the gradient. Every moment stretches the thread of matter thinner. Soon, the difference between head and feet is a gulf, and the body elongates. Muscles tear, bones snap, organs rupture, molecules fragment. Spaghettification claims the structure piece by piece, impartial and absolute. Above, the universe distorts. Stars bend into arcs, galaxies smear into rings. The vault of the sky gathers into a shrinking dome overhead. Time itself fractures, the outside cosmos racing ahead while the traveler's clock ticks steadily onward. To the one who falls, it feels like seconds. To those who watch, it looks like eternity. Two truths, bound together by relativity, both real, both irreconcilable. The traveler falls to their end, while the observer sees them linger forever at the edge. At last, the horizon is crossed. From the traveler's perspective, there is no boundary, no sudden mark of transition. The tearing continues, the compression deepens, the geometry of space itself dictates the fate of every particle. Consciousness has long since faded, yet the matter persists, stretched into a filament, joining the whirlpool of the accretion disk, heated, ionized, transformed into light. Some fragments spiral inward, vanishing into silence. Some scatter outward, carried by jets, to drift for thousands of light years across intergalactic space. What was once a body, once a self, becomes both radiation and gravity, both absence and continuation. The story could end here, with the disappearance of form, but the paradox demands more. For if information is sacred, as quantum theory insists, then something of the traveler must remain. Perhaps it is encoded on the surface of the horizon, etched into the geometry of space-time itself. Perhaps it leaks out slowly, hidden in Hawking radiation, whispered back to the cosmos across eons. Perhaps the universe itself is holographic, and nothing that falls in is ever truly gone, only transformed. We do not know. The final truth lies beyond the reach of our current science. Yet even without resolution, the lesson is clear. Spaghettification is not only a death by gravity, it is a mirror held up to the universe. It shows us that matter is fragile, that individuality is temporary, that existence is woven from threads that can be unraveled. It shows us that the cosmos is both destroyer and creator, both indifferent and elegant. It strips away illusions of permanence, yet it reveals continuity in transformation. For the human imagination, this duality is irresistible. We fear spaghettification because it erases us. We are drawn to it because it reveals the laws that shape everything. It terrifies us because it denies survival. It fascinates us because it grants visions of galaxies bending, of time accelerating, of the cosmos itself unfolding. It is both nightmare and revelation, both horror and beauty. As we close this descent, let us step back one final time. The universe is vast beyond comprehension, and within it, black holes wait, silent, patient, inevitable. They consume suns, they sculpt galaxies, they shape space-time. They are reminders that existence is fragile and fleeting, yet also reminders that everything is part of a greater whole. To fall into one is to vanish, yes, but also to continue in another form, folded into the structure of the cosmos. And so spaghettification becomes more than a fate. It becomes a message. It tells us that we live in a universe where even the strongest forms yield, where even stars can be undone, where even time and matter are stretched into threads. It tells us that we are small, yet also part of something enduring. It tells us that the cosmos is not gentle, but it is coherent, elegant, and magnificent. The final descent, then, is not only for the traveler into the black hole, it is for us as well, descending into understanding, into awe, into recognition. We may never experience spaghettification, but by contemplating it, we confront our own mortality, our own fragility, and our own place in the universe. We are reminded that to exist is to be temporary, to be part of a cycle that includes birth, transformation, and dissolution. And so the book closes with this truth. Spaghettification is not just death by gravity. It is the universe's reminder that we live in a cosmos where even time and matter are torn apart, thread by thread. Yet from those torn threads, the fabric of the universe is continually rewoven in patterns of destruction and creation that extend far beyond us. To contemplate spaghettification is to stand at the edge of the abyss and to see not only the horror of the fall, but the beauty of the cosmos that makes it so.